This is Part 1 of Lesson 9.8, Velocity and Acceleration of Vector Functions. This is the final lesson of Unit 9, and in this we're going to use the concepts that we learned about vector value functions and parametric equations to study the motion of an object along a curve. So as a particle moves along a curve in a plane, we can define its position vector, which we call r of t, using both its horizontal movement, which is going to be our x of t, and the vertical movement, which is y of t, our two parametric equations. And they are both functions of time. By doing this, we can then use the derivatives of r of t to describe velocity and its second derivative to describe the acceleration. So some definitions for position, velocity, acceleration, and distance for a vector value function. So we are given that x of t and y of t are twice differentiable functions of t. So our position of vector of the particle is r of t equals x of ti plus y of tj. So we can define the velocity vector, acceleration vector, and speed at time t with the following definitions, and of course also the distance. So the velocity is going to be the first derivative of our position vector. Our speed then is going to be the magnitude of that velocity vector. Our acceleration will be the second derivative of the position vector, and we can find the distance traveled along that curve by integrating from a to b the square root of x prime squared plus y prime squared, which is the same form of the equation that we used to find the length of a curve earlier in the unit. We're also now going to define what the derivative is as a tangent vector. So the derivative vector r prime of t is going to point in the direction that is tangent to the path traced by the position vector. So using the idea that infinitesimal changes in r over infinitesimal changes in t, and as that delta t approaches 0, we get our definition for our derivative, r of t plus delta t minus r of t over delta t, and we'll be taking that limit as delta t approaches 0. So we will see that that delta r over delta t is going to approach the velocity vector, and it's highlighted in red in the picture. So you notice that at that point P, that is that velocity vector, and it's tangent to the curve C. Please note that when we take the derivative twice or even once, both the velocity and acceleration are again vectors, that they themselves have direction and magnitude. Let's do a couple of examples. So example 1 says, as an object moves along the plane curve C, described by r of t equal to 3 cosine ti plus 2 sine tj, we are going to answer the following questions. So the first question asks us to find the rectangular equation that describes the motion of this particle. So we've done a lot of these, and hopefully you can see that that's an ellipse, but we are going to do this. We're going to do x squared is going to equal 9 cosine squared t, and y squared is going to be 4 sine squared t. And then when we have x squared over 9 plus y squared over 4, we'll have cosine squared plus sine squared, and that's going to equal 1 by our Pythagorean identity. Part B then, we are to find the velocity vector, the speed, and the acceleration vector. So the velocity vector is, going to be the derivative of r of t. So that is going to give us negative 3 sine ti plus 2 cosine tj. So our speed is going to be the magnitude of the velocity vector. So that's going to be the square root of 9 sine squared t plus cosine squared t. Oops, I forgot the 4 there. And then we can find the speed at a specific point by substituting the time in for t. Then our acceleration is going to be the second derivative of r of t. So a of t is going to equal the second derivative of r. So that is going to be negative 3 cosine ti minus 2 sine tj. Part C then says to sketch a graph of the path using arrows to show the direction. So we know from part A that it is indeed an ellipse. So it looks like this. And starting at t equals 0, we'll be at this point 3, 0, and we're going to travel around the ellipse. That's a terrible ellipse. We're going to travel around the ellipse counterclockwise. That's a little better. In this fashion. And then in part D, we're supposed to sketch the acceleration and velocity vectors at the point 3, 0. So if we're at this point 3, 0, that happens when t equals 0. So we're going to substitute that into our velocity and our acceleration vectors. So v of 0 is going to equal negative 3 sine of 0I plus 2 cosine of 0j. And when we simplify that, we just get 2j. So we are going to have a velocity vector that is tangent here. So this is our velocity vector, v of 0 right there. And then the acceleration vector will be a of 0. And when we do that, we're going to get negative 3 cosine 0I minus 2 sine 0j. And so we're going to get negative 3I for this. So that means we are going to have an acceleration vector along that way. So that's a of 0. Example 2. We are to sketch the path of a particle moving along a plane curve given by r of t equals 4 minus t squared I plus tj. Then find the velocity and acceleration vectors at t equals 0 and sketch them on the graph. So what I did was, to sketch the curve, I put my vector in my calculator using the parametric form, and just looked at the table. And you can make a table of values right here if you want to. If you don't have a calculator, you can make a table that has t, x, and y values. And when you do that, you're going to get this curve. Those are the 3 main points that I got. And the nice thing is, on your calculator, you can see it being drawn in this way. It gets drawn in this way. Okay, so now let's find the velocity vector. So v of t is going to equal r prime of t. So that is going to be negative 2ti plus j. And then we're supposed to find the velocity and acceleration at t equals 1. So let me just do v of 1 while I'm here. So I get negative 2i plus j, because the j direction is a constant. Then finding the acceleration, I'm going to take the second derivative. And when I do that, I get negative 2i. So at the time 1, I'm going to get negative 2i because it's a constant, so it'll not change. So I have this. Now I'm supposed to sketch those. So here is my acceleration. So at the point t equals 1, on the graph, if I substitute 1 here, I'm going to get 4 minus 1, so I'm at 3i plus j. So it's going to be like this. That should be touching the curve. Let me use a different color because I already have. So it's going to be like right along here, like that. So there's v of 1. And then my acceleration is going to be like that. So there's a of 1. Okay, one more example in this video, and then we'll continue in the next one. Example 3 says the position of a particle at time t is given by r of t equals 2t to the third plus 3t squared I plus t squared minus 12tj. So I'm supposed to write an equation for the line that is tangent to the path of the particle at the point where t equals 1. So that means I need the derivative. So I'm going to find r prime of t. So that is going to be 6t squared plus 6ti plus 2t minus 12j. And I need to have my x and y at the point 1, so I'm going to do r of 1. So that is going to give me, when I substitute 1 into my two components, I'm going to get 5i minus 11j. So there's my xy. I have 5 comma negative 11. All right, now I need the value of the derivative at the point 1. So that is going to be, whoops, I should have put a 1 in there. So that's going to be a 1. So that's going to give me 6 plus 6, so that's 12i. And then minus, and that's because I'm going to have 2 minus 12 minus 10j. So this is my dx, this is my dy. So my slope m is going to be dy over dx. So that's going to be negative 10 over 12, which is negative 5, 6. So I can write my equation tangent as y equals negative 5, 6 times x minus 5 minus 11. Then part B says, find the coordinates of each point where the horizontal component of the velocity is 0. And we're going to assume that t is greater than or equal to 0. So that means we are looking at where dx dt equals 0. So we have 6t squared plus 6t equals 0. So I'm going to factor out a 6t. So I have t plus 1 equals 0. And so I get two solutions, t equals 0 and t equals negative 1. Cancel that out. And when I substitute that in, I get the point 0, 0. So we're going to finish our discussion in part 2 of the video.